Okay, hello everyone. Welcome back to the sadly last exercise session of the school. Before we get into it, are there any questions? Please have some questions. Yes, question.
If I understand you correctly in the last 5 minutes of the last lecture,
Yeah.
you said that gauge theories are a different way to think about this higher form symmetries. How general and how rigorous is this? So, is for every gauge theory there are always higher form symmetries, or other way around, all higher symmetries are always gauge theories?
Right. No, this is a great question. So this is a quasi-philosophical statement. Let me try to say some formulas to make it sound. So I think that a reasonable statement that you can make is that the point of a gauge theory is actually to describe extended objects. Okay? So let me just now try to, this is not what you normally hear in your textbooks, so let me try to make that sound more plausible. So if you have a gauge theory, you often write your gauge theory in terms of local degrees of freedom, right? Like you write like dA squared. But the truth is, there's something sleazy about this, because the local fields A mu is not, however, a reasonable degree of freedom, right? Because this is not gauge invariant. So why did we do this, right? There's something slightly odd going on here. And one way to think about this is that the real degree of freedom here is not A, but instead the Wilson line, okay? So the Wilson line is the exponential of A integrated, right, over something. So the real degree of freedom is somehow associated with lines and not with points, all right? And from that point of view, the reason why we have this gauge redundancy is to stop you from doing something like having a Wilson line with an end. You can't do that because the gauge redundancy doesn't let you do that. So the point of the gauge symmetry is to somehow sew together these local fields in such a way that where the only objects are these extended things, okay? And so in this exact example, these things are closed because they create electric field lines. Electric field lines are extended objects that move around and do their thing, okay? One thing you might immediately say is that, okay, fine, you can say that, but we do have local operators, right, in this theory. It's not A, but just take a look at F, right? F is a local operator, right? On the other hand, F is really just a very small Wilson line, right? If you take a very small Wilson line over some plaquette spanned by mu and nu, or I'm using the word plaquette, but this is a continuum statement, over some very small square spanned by mu and nu, and you do get F, okay? So I think F it looks like a local operator, but it's just a very small loop. And this is, I think now how I think about gauge theory. I think gauge theories are trying to describe extended objects, right? That's what they were born for. And we sometimes use them outside of that. That's my current philosophical understanding of it. Yeah.
So regarding this, I kind of have in my mind a statement which I completely forgot what the reasoning was about that. Gauge symmetry, when people discuss gauge symmetry is physical or not, that they're kind of also there to tell us how to compose systems. Is this what you meant with
compose systems? Yeah.
Because you're composing local object to something.
Yeah. I don't know, possibly. Is it something like there are different kinds of line operators, right? Like you could, this one is one that is intrinsically a line operator because there's no real way to tear it apart, right? Because if you try to tear it apart, it won't be gauge invariant anymore. You could also do something like, if you say you had a scalar field as well, right? So grad phi square plus m square, blah, blah, blah. Then, you could also imagine doing something like this, integral ds phi of x, on just integrate phi on some curve, why not? This is a little bit different from this one, because this one you can stop at any point, right? There's nothing stopping you from just having it end at some point y. And so are you saying that maybe you need the gauge symmetry to stop you from doing this? Like instead of doing this, you then force a gauge symmetry that makes this one more like that one. Is that what you mean by compose or composing systems? Or?
This was a shot in the dark because I kind of forgot what
All right.
you meant by this.
Yeah. Okay. I confess I'm not sure either. Yeah. I don't think I really know either. Yeah. But yeah. And I realized I didn't fully answer your question, actually. Whenever you have an extended object that has some integrity or some reason for existing, then it will have a higher form symmetry. So therefore, it really basically means pure gauge theories always have a higher form symmetry. And then gauge theories with matter, in those things, the extended objects, the Wilson lines or whatever can end, and then they often don't have higher form symmetries anymore, but still you kind of feel like the dynamics is about these objects, and then you're trying to, deal with them even though they can end, and so on. Yeah.
So can you reformulate electromagnetism in terms of just like strings or something in this way?
Yeah, so to be honest, I think we kind of did in these lectures, though I didn't emphasize it. You see, what I said was that there is a higher form symmetry that counts these strings, right? And then I said that higher form symmetry is spontaneously broken. Then I wrote down the most general effective theory for the breaking of that spontaneous symmetry, and it was this. Okay, and now we're done, So I think that you can do that and you get normal E and M, Yeah, whether that's satisfying or not is a different question. But the thing that's different is that because the symmetry is spontaneously broken, the strings have condensed. So it's a lot like if you have a theory of particles and you try to use that to describe, the physics of a Bose condensate, right? Really, you don't describe individual particles anymore. Instead, the right degree of freedom is the phase of the overall condensate. This is the higher form version of that. You don't describe the strings, but rather the modulations of the sea of strings, and that turns out to be described by that. Yeah, good questions. Other questions? I'm enjoying the quasi-philosophical character of the questions because it means I don't have to do a detailed calculation on the board. Any other questions? Yes?
Can you give some other quick example of system with non-immutable symmetry?
This is good. So another example that I can give, let me just erase this and use this, is again the 2D Ising model. I'm going to get at the details of this wrong, but the 2D Ising model has a duality. So I'm going to start by explaining the duality of the Ising model, and then I'll explain the non-invertible symmetry. So the 2D Ising model has the following Hamiltonian. We wrote this briefly on the board. It looks like this, where you have a bunch of spins on a lattice. Okay, so on the sides of the lattice, you have a bunch of spins that are plus or minus 1. Okay. Now, it turns out that you can do a duality on this. Okay. This is called Kramers-Vernier duality, except now in 2D. And it's closely related to the example I told you. In 3D, if you do Kramers-Vernier duality on this, you get the Z2 gauge theory. In 2D, if you do Kramers-Vernier duality on this, you get the same Hamiltonian back again, except that the temperature is different and the degrees of freedom are different, but it looks the same, is what I mean. Okay? So if you run a duality on this, then what you find is that you naturally get degrees of freedom who are valued on the dual lattice. I should use a different color, maybe. You naturally get some degrees of freedom who are valued on the dual lattice and not on the lattice. Okay? And these are now the sigma I twiddles. So these guys are the sigma I twiddles. All right? And beta is related to beta twiddle in a way that's sort of backwards, in that small beta is high beta twiddle and vice versa. So if this is beta twiddle. Okay? It's probably not actually like that. I'm just trying to show that the low beta maps to high beta twiddle and vice versa. Okay. So this is an interesting statement, all right, because it means that the same physics you can write in two completely different ways with a very non-trivial mapping of the temperature, okay, to itself. Now, okay, I have to say a few more words about this before this makes sense. So this maps high temperature to low temperature, okay. So what that means is that so this is a normal symmetry, so we can just talk about its breaking. If we have a low temperature phase, then we will, in this frame, when you have beta being high, so it's low temperature in this language, then typically you have a magnetized phase. So that means that the VEV of sigma is not equal to 0. In other words, most of the spins are lined up. This is the ferromagnet. Okay? But because of this fact that beta and beta twiddle are sort of inverse of one another, if this is in a low temperature phase, then this will be in the high temperature phase, right? So in other words, if this has spontaneous symmetry breaking, then this guy will not have spontaneous symmetry breaking. Oh, I messed that up. Damn it. Will not have spontaneous symmetry breaking, okay? This symmetry is going to be unbroken. So this sort of indicates something interesting is happening, all right? Okay. Now, these are all just words in general about Crummers linear duality. And now let's think about this thing. So if I tell you that there is only one phase transition in this model, okay, then a phase transition is a very singular point. And if there's only one of them, that means it has to happen when beta equals to beta twiddle, because the Hamiltonians are the same, right? So they have to both report the phase transition. So in other words, that happens at the intersection of this curve with this curve at a certain point. And from that, you know the phase transition happens at a particular point, okay? But because it happens at a particular point, that means that when at the phase transition point, so at beta critical, which equals to beta twiddle critical, this is a self-duality, right? It maps the theory to itself, okay? So now you can imagine doing the following thing. Let me do the duality in half of the space, okay? And glue it to itself in the opposite duality frame. Because it's a self-duality, you can do that, right? Why not? That defines a line in your space where nothing actually cares about the line, so it defines a topological line, okay? This is called a self-duality defect. Let's write that down. And you can see, so the self-duality defect means dualize in half the space. Okay? And the boundary of that half space, or really any two-dimensional region, to be honest, but you get the idea, defines some line, and the self-duality defect is a function of that line. We just call it SD as a function of C, and it's topological because the theory is going to itself, okay? This defines a topological line, so it's like a symmetry, but it's a non-invertible symmetry, okay? This is the simplest one, to be honest. This is simpler than the axial symmetry one that I told you about, but it's simpler, but the model is maybe less familiar to people, so that's why I introduced the other one. But yeah, this is, I think, a very interesting thing. Yeah, that was a lengthy explanation, but this is another example. I'll just tell you a few more things about it. You see, the sigmas get sort of changed when you change the duality, right? It turns out that if you take a sigma and you drag it through, take a spin and drag it through the self-duality line, on the other side, it's not true that sigma gets mapped to sigma twiddle. Sigma gets mapped to an object that has a tail attached to it, okay? So when you drag, that sort of thing can only happen when the symmetry is non-invertible. Okay, so that's another example of the sort of thing that can happen. Things acquire tails, and that's one thing. Okay, good. So that was a bit lengthy, but this is another example. Any questions about this self-duality defect? Yes? Yeah.
Those two examples you provided us,
Yeah.
they all look like an reinterpretation of things relatively new. So
Yeah.
what is the biggest gain from this?
Yeah, so I think that the gain is that you learn that there are once you think about them in this way, you realize that there are new things that you can do, okay? So I'll give you a few examples that I like. So for example, I proved to you a Goldstone theorem, right, earlier on. So you might ask, is there a Goldstone theorem for the axial symmetry with the anomaly, with the ABJ anomaly? And until recently there wasn't, but now that we knew about this topological defect, you can now try to use the way that I proved the Goldstone theorem. You're inspired to use that idea for the new axial symmetry. And I mean, it's the same axial symmetry, but you're now inspired to use it for the axial symmetry because you're reinterpreting it as a kind of messed up symmetry instead of as a whatever it was before. And so that you can do that, for example. So we have proven a Goldstone theorem for the axial symmetry, and maybe you could have done this at any time, but it didn't occur to us to do it without having this language. And I think that's really the thing, that you realize that your intuition from symmetries can be sort of moved over to this new way of thinking, and you get inspiration to do new things. So I'm not sure it's always a thing, do you need the new tool? Or maybe if you're smart enough, you don't need the new tool. You can just immediately leap to the result. But at least for many of us, I think having the new tool and comparing it to how I normally think about symmetries is very helpful. Yeah. And so as a result of that, there are many new results, many new constraints on quantum field theory that are coming from this sort of thing. And I think each of them, if you really stare at it, you're like, oh, well, I didn't need these words. I could just have derived the result. And it's true, but you need to be inspired to derive the result. And I think that's really the value of this. Yeah. So yeah. Some other examples that I like are the stuff I told you about hydrodynamics at the end. This is again, it's my own work, but I'm fond of it because it is really quite useful, to be honest. Like I think you didn't need all the words, but you need a lot of them, to be honest, to get this thing. And it seems like it does work. There were some people who did some numerical simulations, and their results, they thought that their results did not agree with hydrodynamics, which is really weird because honestly, if you do a classical simulation, you're simulating some classical system, it should agree with hydrodynamics. I mean, hydrodynamics is really general. It applies to, if you put a bunch of like balls in a box and shake it around, I mean, it's described by hydrodynamics. So it's weird that your simulation wouldn't agree with hydro. And it turns out that it did, but it's just the normal hydro that people were comparing to sort of kind of assumed a weak electromagnetic coupling, and they didn't have that. And so if you use a more general language, then it does work. So that was another thing. Again, I'm just telling you about my own work because I'm fond of it. But it's another thing where I don't think we could have gotten that result without the higher form symmetry stuff. So yeah, and some other work. Okay, I could keep advertising lots of things. One more thing that I'll just talk about is if you look at QCD in 2 dimensions coupled to a certain kind of fermion, then there's an interesting phase structure. It doesn't confine when you expect it to. And there's a reason why. It's because there's a non-invertible symmetry present. And Zohar Komargodski and company, they explained this non-invertible symmetry and they used it to explain the phase structure. And again, maybe you didn't need it, but it's a nice picture, you know. So there's many things like that, I think. Yeah, but it's a good question. Yeah. Good. Other questions about anything that we've discussed? The last exercise that I assigned you is probably too long to do in the 20 minutes that we have left. Yes?
Maybe it's so stupid, but can you make sense of gauging these non-invertible symmetries?
Yeah, no, it's not stupid at all. So gauging higher form symmetries, you definitely can. Gauging non-invertible ones is complicated. People are thinking about this. There have been some very recent papers that I believe basically do make sense of this, but I should say that I haven't really understood them yet, so I shouldn't say any more. But I think that you can do it. You have to think about what you mean by gauging. I think you have to really think about that very carefully. So for a discrete symmetry, it's a discrete normal symmetry, when you think about gauging it, what you really typically mean is you're inserting a network of topological defects that implement all possible transformations of those symmetries. That's what it means to gauge. And so viewed in that way, you can generalize that to non-invertible symmetries as well. And then this is really interesting, and it's just not something that I know too much about. But I can show you some papers of people doing it recently. This is, now we're really getting up to the cutting edge of what people are currently doing. Yeah.
Sorry, can you just repeat what you mean by gauging?
Yeah, so if you are gauging normally we only gauge continuous symmetries. At least normally meaning in elementary physics, we typically only gauge continuous symmetries, right? And what that means is you basically couple to something that couples to you couple in a field whose source is the current, and then you sum over all values of that field, right? You do A mu, J mu, and then you integrate over all A mu, and that sort of sources the current in all possible ways. Now, something else you can do is gauge a discrete symmetry, okay? And that's not done as often, but it's a very well-posed procedure. And again, what you want to do is you want to basically sum over all possible ways of sourcing the conserved thing, which here is a charge, right? There's no current anymore, there's only a charge. So what you really do is you sum over all possible ways to insert these charge defects that I talked about. That's what it means to gauge a discrete symmetry. And when you phrase it in that language, then you can think about doing it for non-invertible symmetry as well. And people have done that to some degree, but I'm not following this extremely closely, so I shouldn't say anymore. Good question. Maybe someone else here. Is anyone else here following this more carefully? Okay, probably not. Yeah, Pablo probably has. Yeah.
Yeah, I can basically say that they are struggling to get
Okay, right.
this moving forward.
Yeah.
They are finding that sometimes you simply cannot insert this mesh of
Yeah.
for example, that non-invertible symmetry you say the one of the
Yeah.
you cannot gauge.
That's right.
And they call it anomalous in that sense.
That's right, absolutely, indeed. So this was relevant for Pablo's recent nice work on the, so what Pablo recently did was use this to look at entanglement entropy, sort of graded by the symmetry action. But what, there's something weird about this in that you can't gauge this one, okay? And then, as Pablo mentioned, when you can't gauge a symmetry, then you sometimes say it has a Toast anomaly when it's a normal symmetry. So maybe this is a way to describe what it means for a non-invertible symmetry to be anomalous. A candidate definition is that you can't gauge it. That's a possible definition, and now I think you're seeing if that's a useful definition or not. People are still studying that. Yeah.
I think that's a perspective of like Shefanonik and stuff, but I just tried to remember the lecture that we did.
Sure. Oh, who?
Sakura Shefanonik.
Oh yeah, that's right. Indeed. Yes, absolutely. Yeah. Good. Other questions? Any other questions? I think it's been a long it's been a long week. I understand if people don't have any other questions. Let's see. So let me think about this. Okay. So what should we do with the last time? There are a few more exercises that I could do. Let me think about what a good one would be that's maybe suitable for our current level of energy. One thing we could do is, today I quantized this theory in a Hamiltonian formalism. I did it kind of quickly. I didn't really quantize it. I just kind of said, here's what happens. Shall I go through how you would go about quantizing this theory? This is a Gaussian theory, so it's not that hard, but there's some calculations. Does that sound reasonable? Okay, I'm seeing some nodding. Let's do that. This again, I haven't actually done. I just wrote it as an exercise, so hopefully it will work out. Okay, so the action for the BF theory is this: In over 2 pi integral over M4 B wedge dA. Okay, so let's quantize this the way that on the manifold that I talked about, where we have time cross S1 cross S2. Okay, and let's give everything coordinates. Let's call this one x, and let's call these coordinates theta and phi in the normal way. Okay. Now we're now going to, and this is time, of course. This is t. Okay. So now let's start by writing down the terms that appear in this action. Okay. So what we have is this. There's an epsilon here, right? So we're only going to get all fully antisymmetric combinations of things, right? So what we're going to get is something like BT. Sorry, I forgot what was a 2 form. It was a 1 form. B is the 2 form. A is the 1 form. So what we're going to do is we're going to get some term like, for example, B theta phi dTAx. That's one sort of term that we can get, right? And then we're going to get terms like, let's see, this is somehow difficult. To be honest, this is the interesting one. All the rest I'm writing down are somehow not going to matter, as we're going to find out. But we have terms like this, A phi, and then, okay, you get the idea. It's the rough structure is the following. Epsilon I, j, k, these are the 3 spatial directions, right? And then we have B, I, j, dt, a, k. All right? This is the rough structure. And then there are also terms where the derivative is not on the derivative is either not dt or is not on, okay, let's write down some more terms. So we could also get, for example, something like bti epsilon ijk dj ak. Okay, we can also get terms like this. I don't really want to think about these terms right now. So let's gauge fix to the following gauge. At equals to 0. This is what? Coulomb gauge, I think, right? And then also we do the higher form version of Coulomb gauge where bti equals to 0. Okay. So after doing that, we only have the spatial components left. All right. So that means I can ignore all of these terms. And now the only terms that survive, therefore, are the ones with the time derivative is acting on the variables. Okay? Okay. So we have lots of terms like this. And now let me work out, so basically the term, it looks like this. This is the Hamiltonian. Okay? And I'm expanding that out to get lots of terms. We'll see in the end only this one will matter. Okay? Okay, but the Hamiltonian is really this. Okay, does that make sense to everybody? Okay. Now, let us work out the canonical conjugate to A. Okay? So when you're doing normal quantum, like Hamiltonian quantization and quantum field theory, the canonical momentum to some variable is basically delta L, delta that variable dot, right? Okay. So in this case, the canonical momentum to AI is epsilon ijk bij. Wait, sorry, that's ak, excuse me. So the variable conjugate to ak is epsilon ik bij. Does that make sense? All right. This just comes from this taking this derivative. So so notice what's happened here. The spatial components of A and B are conjugate to each other. Okay? So you can write down the following commutator. This is an equal time commutator. So here by x, I mean a point in S1 cross S2. The equal time commutator of these two is basically epsilon ijk times delta of 3 x minus y. Where I'm doing the indices all wrong, but you get the idea. Okay. Actually, I don't know why I did that. Let's just put them down here. Okay. Now it's actually correct. Okay? Because A is conjugate to B. All right? This sort of thing happens for first order systems like this. You typically get that the field is conjugate to another field. That's normal. Okay, everyone happy with this? All right. Now, to continue with the quantization, actually I'll just use this, sorry. To continue with the quantization, I should point out that I did something a little bit too quick, in that I set AT equal to 0 and BTI equal to 0 by gauge fixing, but actually we should make sure we vary it first, right, in the action and then set it to 0. That's the right way to do these things. So if you vary AT, then if you go through this, what you're going to find is that the equation of motion, delta AT equals to 0, is epsilon ijk di bjk equals to 0. Okay, that's the way. I think I might have, did I erase the term? I think I erased the term, but it was there. You know, it's this is the way that these structures appear. And similarly, the equation of motion, delta bti equals to 0, gives you that epsilon ijk djak equals to 0. Which means that the spatial field strength, okay, viewing these as spatial two forms, the spatial field strengths of all these things are 0, okay? Which means that, again, this is what I was saying earlier, that there's no information in the spatial dependence of the field, okay? So you can only get something interesting if you integrate it over some sort of non-trivial cycle. Anything else doesn't have any information in it. Okay. So this was just motivation to instruct us to think about these objects, the Wilson line and the Toth line, which I remind you were. Oh, sorry, I have done something terribly wrong. This is actually important. Okay, so there's a factor of n here that I left out. Let me put this back. This is going to be crucial. So I said pi ak is dl dak dot. And I said this is equal to this, but I left out this n. Okay, this is in front of everything. This is important, okay? So the canonical momentum is n times b, right? Which means the commutator of A and B is equal to 1 over n. There's some 2 pi's in there that I'm not going to try to get right, but it's 1 over n times epsilon ij. This is actually crucial, so sorry for leaving that out, okay? All right. Good, now let's come back. All right. So, so we've been motivated to look at. So the claim is now the only real information is in topologically non-trivial things. Okay. So therefore, the only thing that we really have to look at is the integral of e to the ia. Sorry, e to the ia. Okay, over the non-trivial one cycle, which is that S1 in this case. All right, and also b of two manifolds, this is a C1, which is the exponential of integral over the S2. So I don't know why I wrote it like this. It's just one of them. Wow, sorry, I'm really forgetting my notation. G of S2, and you integrate basically B over this two manifold. Okay? I'm mixing notation like crazy. So what this means is that this is just basically ax, okay, times the length, and this is basically b theta phi. Okay. Okay. Now, is this going to work out? I think it will. I'm just a little bit nervous about the factors now. Okay, but we'll worry about the factors in a second. Okay. So now what I want to do is I want to work out the commutator of these two things using that relation over there. Okay. So yeah, okay, it does work out. Okay, so, let me just actually write this down in coordinates now. So this is actually d, what did I call it? X, ax. And this is actually d theta, d phi, b theta phi. Okay, it's literally these two integrals. Okay, viewed as integrals. Okay. Now, I want to now work out the commutator of these two things. So what do? So I write down w times g, okay? Which now, these are all quantum operators, so I have to be careful about the operator ordering, all right? So that's exponential of I times the integral dx ax times the exponential of I integral d theta d phi b theta phi, okay? Now, I want to figure out what they are in the other order, okay? The way to do that is to use Baker-Campbell's-Hausdorff, BCH, to bring the two things both into the exponent, right? Now, if I remember correctly, e to the a, e to the b equals to e to the a plus b plus the commutator of a and b, plus an infinite series of other terms. And there's a factor, okay. In this tutorial, all factors are wrong, so there's a factor there. The only factor that's correct is the n. The 1 over n is correct. Every other factor is wrong. I think it's half, to be honest, right? Do people agree with that? There's a half there, right? Yeah, okay, good. Some people actually know formulas. Yeah, good. So there's a half there. So let's use this to combine these two things, right? So what we get is that this is therefore equal to the exponential. Now I bring them both up into the exponential. And so we have this plus the thing with b, okay? But, and now here's the fun part, there's a commutator term, right? Sorry, I don't know why I closed the exponential. There's a commutator term, which is something like a half times the commutator of these two things, right? Okay, so let's work that out now. This is actually interesting. So, so the commutator takes the form of dx, d theta, d phi, but this makes it look like we're integrating over all three volume. It's not that, okay? I stress that what's happening here is we're integrating over the S1 and we're integrating over the, what's the right way to put this? Okay, let me just keep going and then it'll make sense. It's not, okay, sorry, I'll write another formula and then it'll make sense. And the commutator is between ax, b theta phi, okay? It's like this. Now, the ax is integrated over the S1, and the b theta phi is integrated over the S2, and it's only where they collide that they get a contribution from that delta function. Okay, they hit at one point. All right, so you just get a 1 from that delta function. All right, but it's not a 1; it's a 1 over n. Okay, and so this whole thing ends up being just an overall phase, which is just a number. It's e to the I over n. I lost the I somewhere, but there's definitely an I that I have lost somewhere. No, sorry, yeah, of course. This I is the famous quantum mechanics I. There are many I's in this topic, but this is the famous quantum mechanics I. That's the one that creates the I here, okay? So there's an I over n, and then there's a series of numbers here, which when done correctly would give you 2 pi. Okay. So actually, I've only done half of it. I've told you that Wg equals to something that has them both in an ordering independent way times e to the I over n. Okay. And then now what you want to do is, of course, you want to do the opposite one, right? Which again gives you the same thing, something of like a plus b with the thing in the opposite way, e to the minus I n. And then you combine the two phases into one, and you find at the end of the day that Wg equals to e to the 2I over n times GW, where when you do the numbers correctly, it turns out to be 2 pi I over n. Okay? Does that make sense to everyone? This is a bit fast. Yeah, this is an understatement. Yeah, yeah. Yeah. Yes? Yeah. No, this is correct because the commutator of A and B is already, the way BCH works is you get more and more commutators of the thing, right? It's like, okay, the next term is something like A commutator A comma B, right? But commutator A comma B is already a number. And so all the higher ones are 0. So this is exact, yeah. The only approximations that I have made are when I set 2 pi equal to 1 equal to 4, you know, all those things that I did, yeah, yeah. So, okay. I regret not actually writing this out before, but okay, it kind of worked out. You see the structure? The information comes from the BCH term here, which comes from the canonical commutation relation of A and B. That's where it comes from, and one can do this, the rest of this stuff, right? Yeah. Yes? Yeah, sorry. This is now, we're now in Lorentzian. That's right, yeah.
I guess there should be no I in the action, right?
Yeah, you're right. Yeah, absolutely, you're right. I mean, I sort of dropped it anyway. When it was important, I just quietly dropped it anyway. Yeah, indeed. So there's no I there. Yeah. So here I dropped it already. Yeah, exactly. I have a self-correcting attitude towards doing math. Yeah. Okay. And so this is the main result. Okay. So I was very quick and not very precise here, but you can do it carefully, and this is really what you get. The Hilbert space is really determined by this stuff. Okay. Okay. And from here on, everything is correct. Right. Whew. Okay. Good. Other questions? We're almost done, I think. Yeah, any other questions? Yeah. Okay. Yeah.
You're talking about Zetan
Yeah.
description. Okay. I have the description. This is because we had SVN.
Yeah.
So would something crucially be different if we start from, I don't know, spin and H0? Because then the center is not just Zetan, right? Something.
Well, what is the center? I don't actually know what the center of spin n is.
I'm not sure.
Yeah.
For spin 4 is like Z2 times Z2 or something.
Okay. Then Z2 times Z2. To be honest, these are the cases that cause a little bit of, people have studied very similar cases, and one should look at this. I guess because it's a product group, you should worry a little bit about it. It's not, what's the word? It's not simple. Is that the word I'm looking for? Sorry? Cyclic, maybe. There's like, it's like not minimal, right? There's two, it's a product of two minimal things, and then those are the ones that you have to think about carefully, basically. So you should think about it carefully. I don't know what the answer is, but people have studied these. You can get interesting wrinkles, actually. You know, there's interesting representation, theoretical things that happen. If you force me to, I'd probably say it's like 2 copies of that, but I suspect that maybe there's a little bit more going on. But it's for any abelian group, you can figure out what's happening, yeah, to spend some time on it, yeah. But yeah, cyclic, yeah, maybe that's it. Yeah, anyway. Yeah. Good. Yeah. Is that yeah, okay, very good. So it's not indeed. So this is not cyclic then, right? Yeah, good. Anyway, okay. Any other questions? I admire everyone's stamina. I mean, it's been a long thing. I feel like let's see. It's possible that Martin will come back at the end of this, right? Is that correct? I sort of think that we should. Do you know? Yeah.
We should finish with that.
Yeah. I feel like I don't want to finish without him. That was the point that I'm making. But yeah, is Martin going to come back at the end? Oh yeah. Hey Martin. Anyway. Yeah. Okay. So yeah, question. Yeah.
So, I mean, a Wilson line is just about a field somehow, and these topological operators are just to measure them, but they're not, or are they really deforming the space somehow? Because I think once we had this question about trivial topology, and if you said it's boring because we don't have our topological operators, so are they really deforming is this really a defect in space-time, or?
So I think that the real question you're asking is what is a defect in the space, right? You're really asking what is defect in space-time. So I mean, I think that I call them a defect, but that's really just a name. I mean, I think that all one can say is they do something, and then you characterize their commutation relation. So for example, in this TQFT, what they do is they raise they act on the ground state in a calculable manner, given by this. And now what you want to call it, I think, is basically up to you. So I don't know if that's very helpful, but that's I think it. Like, maybe a question I can ask, which is related, is, say you acted a local operator here, okay? Is that local operator deforming the space-time? Well, it sort of depends. It's sort of a matter of taste, right? Like, it does something. It creates a disturbance there. It can be a very violent disturbance. I wouldn't say it's deforming the space-time. I just say that because we're not looking at a gravity theory, so nothing is deforming the space-time. But it's certainly creating a violent disturbance, right? This thing, yeah. Sorry, what? Yeah, exactly. So I would say that it's creating a disturbance, and this creates a disturbance along a line and not along a point, but it's still a perfectly fine thing. So maybe I will say that there is a technical distinction, actually, that nowadays the word defect, people are using it in a slightly more fine-grained sense. So basically, I have called anything a defect, to be honest. I distinguish topological defects from non-topological defects. Hey, but I called I called everything a defect. Just if it was defined on some extended manifold, I called it a defect. But there is actually a more fine-grained notion of defect, which I'll tell people, which is that nowadays, you see, imagine if you have a defect, say you're in Lorentzian, okay? If you have a defect living mostly in space, okay, that's fine. It's living mostly in space, okay? But sometimes you can take that defect and rotate it to live with one leg in the time direction, all right? Now, if you do that, now you can quantize your theory in the Hamiltonian sense, the way that we just did over there, all right? And you will generically get some extra degrees of freedom that live on this defect now, because it lives in time, so it'll have some extra degrees of freedom that live on it, and you should quantize those guys and look at the degrees of freedom that they give you, all right? And that will define a new Hilbert space, like the Hilbert space on the defects, all right? Now, sometimes what I just said is fine, in that you can rotate it so it lives in time, and you get a well-defined defect Hilbert space, and sometimes it's not fine. It doesn't work out, in that the Hilbert space you get on this object is like infinite dimensional or something, like something bad about it. You don't like it for some reason. Nowadays, people are calling it a defect if the Hilbert space is good, and they're calling it something more general, like object, if the Hilbert space is not good. Okay. And so this is actually sort of important. Like, for example, at the very end, I mumbled some things like. I said that you get this rational cover of the circle when you try to do this non-invertible symmetry. Those are all good. You can look at the Hilbert space you get on the thing if you point it in time, and you get a nice Hilbert space. But we wanted to prove a Goldstone's theorem, and we did something different. Okay, and we actually got a U1 non-invertible symmetry. But in a sense, though I could use it to prove what I wanted to prove, it's not good in that if you rotate it to point in the time direction, it gives you a bad Hilbert space in that it looks like it's infinite dimensional, okay? So some people would characterize that not as a defect, but as an object because of this technicality. So this confused me for a while when people were like, no, it's not a defect. And I'm like, what do you mean it's not a defect? I mean, it's sitting there, right? Like it's a defect. But no, this is a new fine-grained distinction. So this might be useful if you go to the literature. This is a very technical meaning of the word defect, but I think it's yeah. Okay. So I realized that it's the end. So I think that now is a good time, first of all, for all of you to thank yourselves. Thank you for all of your wonderful questions. We really enjoyed this, so please give yourselves a round of this thing that we do. Yeah. Okay. And now, I think that Nella and I both want to thank all of the organizers for inviting us to be here and for organizing this thing that was really, really, really fun for both of us, I think.
Right, yeah. So thank you so much for the hospitality. Is that the word?
I think hospitality is the word,
hospitality,
yes. Yeah.
And for doing such a great job organizing. So we would like to ask for a big round of applause for Katharina, Jakob, Federico, and Martin.
Normal, yeah. Yeah.